Okay, this is lesson 16 of module 4, 8th grade math. And in this lesson, we are going to continue talking about slope, and in particular, we're going to work on computing the slope of a non-vertical line. So in the last lesson, we developed sort of a definition of slope, which is a measure of steepness, and it's also a measure of the rate of change. So as x changes, y changes, and so slope measures the rate of change of an equation or a graph. Okay, so using what you learned in lesson 15, let's look at example 1. Determine the slope of the line that has this graph right here. And while you're at it, you can look at example 2 as well if you're feeling confident. So pause the video and then come back and we'll look at example 1 and 2 together. Okay, so looking at example 1, we can find a place on this graph, and we can find it right here, where we can find a horizontal distance of 1. So we can start there, and that leads up to a point on our graph also that we can read right there. So these points will allow us to determine the slope, because what we did in the last lesson was we called this point Q, called this R, and P, points on the line. So on this graph we can find points P and R fairly easily. We can tell because the line crosses at a point on the grid where we can, basically we can read the coordinates of this point would be 3, 4, and the coordinates of P would be 2, 1. Okay, and the horizontal distance is 1. So we marked off that, and we know that this distance here, QR, is going to be our slope. Because if we take this triangle and translate it so that Q is at the origin, we would have this drawing. Let me change color here. We'll do it in green. We would have this drawing. We'd have P, Q, and right up here, R. We would have this triangle. So that would be R prime, Q prime, and P prime. So we've translated that slope triangle down to the origin, where we can just read the slope. So the slope of this graph, is 3. Okay, if you didn't get that, then you might need to go back and review lesson 15 or some of the examples, or possibly the homework. Maybe go in more detail over the homework and looking at the solutions for that. Okay, so let's look at example 2. Okay, so on example 2, again, we're looking for 2 points where we can that are on the line that are also readable on our graph. And so we have this distance. I'm seeing a distance of 1 right here, and I can draw that slope triangle just like so. Okay, so this distance, this point would be P. R is the other point on the line, and there's our Q, and the Q, remember, is picked because it's at directly below R and directly to the right of P. Okay, so again, we're going to translate that triangle down to the origin so that we can read off the slope value, which is just the length of QR. That triangle would end up right here after its translation, and we can see that the slope is 2. So the slope of this graph is 2. All right, let's look at example 3 now. And example 3 says, what is different about this line compared to the last 2 examples? So think about that. Pause the video if you need to, and then come back. We'll talk about it. Okay, so the thing that's different about this graph is as I look along this line, I'm having trouble finding, see now there's a point where I can tell the coordinates, but if I go over 1 and up, I'm not sure what that value is, so I won't be able to determine the slope m, and that's true wherever I go. When I go over a distance of 1 from a known point, I can't read the value. So this is a little different, but obviously this line has a slope that we could find. And so we need to develop a method for finding the slope when we can't get that horizontal distance of 1 on the graph. Okay, so let's look at how we could do that. Okay, so this diagram will help us to kind of review what we talked about in lesson 15. So here you see a line, L, and we have points P and R on the line. P has been placed at the origin, but it didn't have to be, but for our purposes, there it is. And Q is the point directly below R on the x-axis, and we've chosen Q so that PQ is 1, okay? And you can follow at this perpendicular line right up to R, and we said that this distance QR is the slope, okay? The other thing that we talked about was that the slope we saw on some graphs is the rate of change, okay? So this shows the rate of change for 1 unit. Okay, so slope can be thought of and is actually equal to the unit rate. So we had the mowing the lawn problem or situation. So the unit rate would be how much lawn could be mowed in 1 minute. How many pages could be typed in 1 minute. So in 1 unit of time. Maybe it's how many boxes could be packed in an hour. So that unit rate for one amount, one segment of time is the slope of the graph. And so so we can read that right here. It's this distance QR, and remember we use the letter M for that. So what we're trying to do now is to figure out how to compute the slope when the horizontal distance is something other than 1. Okay, so to do that, we're going to look back at example 2. So in example 2, we found that the slope of the graph was 2, and we drew a slope triangle. I drew one right here. You may have put one somewhere else because you might have found this one over here, or you might have found that one, or that one. So wherever we draw these triangles on this line, we notice that for every 1 unit of horizontal change, we get 2 units of vertical change. So there's another 1 and a 2, and another 1 unit and 2 units. So all of these are giving us the same result. So it looks as though it doesn't matter where we choose along the line, our computation of the slope is going to be the same, and it's going to be 2. Okay, so, but I want to go a little bit further and look at what happens when we look at a horizontal distance other than 1. So I'm going to draw another slope triangle, but I'm going to come across here, this time 2 units of horizontal change, and finish the triangle up to the graph here. And notice that there's 4 units of vertical change for 2 units of horizontal change. So let's look at what that looks like mathematically. So let's look at this diagram another quick minute, and then we'll go back to example 2. So because the slope is the unit rate, that means it's this ratio. It is the distance QR over PQ. And in the case of PQ being 1, the slope is just the distance QR. So let's go back to example 2 and look at what we have. So we've said that slope could be thought of maybe as that ratio QR over PQ. And here's our Q, P, and R. So we can see that the slope, the distance QR of 4 over QP or PQ, which is 2. And if we use one of those other triangles, we have the 2, the QR being 2 over PQ of 1, 2 over 1. Both of those give us a slope of 2, which is what we calculated originally. So we see that these ratios are the same on these triangles. So if we want to, you can think back to where we've seen that before, and you might notice some similar triangles going on here. So let's look at where they are. I'm going to clean up this diagram a bit. Okay, so here are 2 triangles. You can kind of see the blue and the red, and we can show that these triangles are similar by the angle-angle criteria. And so see if you can see where the 2 angles are that are congruent, and actually all 3 are. But we know for sure that both of these triangles have a right angle here that correspond. And then they share this angle that the line makes with a horizontal grid line. So this angle here, they both share. They both have the right angles. Therefore, they are similar triangles. We could also show that these angles up here, whoops, that wasn't what I meant to use, that the angles up in the corner are congruent by because of the parallel lines. So this angle is congruent to that angle because we have parallel lines cut by a transversal, and so these are corresponding angles. So we've actually shown all 3 angles of these, the small triangle and the large triangle, to be congruent. So therefore, the 2 triangles are similar. So why am I saying all this? Well, if these triangles are similar, then the ratios of corresponding parts will be similar. Okay, so what this means is important. It means that we can calculate the slope using any 2 points on the line. It doesn't matter where they are. The horizontal distance does not have to be 1. So we can use any points on the line. Any 2 points, we could draw these similar triangles with the unit, basically the unit triangle. The ratios would always be the same, and we would get the same calculation for the slope. So maybe some of you already figured that out for example 3 and have calculated the slope. So if you hadn't, why don't you see if you can find 2 points on the graph of this line that intersect grid lines where we can tell what the coordinates are, which will help us to calculate the slope. We could choose any 2 points we want, but it's easiest to choose points that we can read the coordinates off of to find the distances. Okay, so go ahead and do that now and come back. Okay, so I'm going to draw a few examples of what a slope triangle could be here. And if I start at the point 2, 1, right down here, I can come across, and notice that I can come up to the line again right here to a known point, which is 5, 3. So I've got 5, 3, and I've got 2, 1 right here. And from that, I can calculate the slope, because this would be my P, my Q, and R. And the ratio of QR to PQ would be, let's write it out. So M is equal to QR, distance QR, over QP, which would be 2 over 3. Okay, but maybe somebody else chose a different set of points, so let's see what that would look like. So maybe I did, let's pick a different color for the next one. I could have done from here all the way up to that point, which is the point 8, 5 is equal to 5. And if I do that, then my slope is the same ratio, QR over QP, but I would have this distance here. So I would have 4, and the horizontal distance would be 6, and that would be my slope. But notice that these two ratios are equal. So whichever triangle I choose for my slope triangle, it's going to be similar to all the others, and they'll give the same ratio for QR over QP, or the vertical distance divided by the horizontal distance. So in this case, 4/6 is equal to 2/3. So both of those are measures of the slope. Okay, so let's look at the exercise that you have in your notes. And go ahead and look at that independently and then come back and check your work. So it's 3 parts. First, you select any 2 points on the line, label them as P and R, and you want to pick points that you can determine the exact coordinates of. And then identify the coordinates. And then part C, find the slope. It says using as many different points as you can. So once you've done that for 2 points, then maybe identify a couple more and verify that the slope is the same regardless of which points you choose. Okay, so here are 2 examples of what you might have come up with. So for my first triangle, I chose these 2 points that I labeled in purple, and -2, 1 and -1, 3, and I drew the slope triangle for them and saw that the slope was 2 over 1. Here's the 2 and here's the 1. So that was actually a point where I could find that unit distance, unit of 1. But it's not necessary, because I could choose this point and this one, and my vertical distance was 8 and my horizontal distance was 4. And the slope of the line, notice these 2 ratios are equivalent. 2 over 1 is the same as 8 to 4. They both have a value of 2. So the slope of this line is 2. Okay, so we want to show that for any 2 points, we can calculate the slope. And so this diagram shows just 2 random points on the line, P and R. And we're going to use the convention that we're going to label these points with their coordinates in a way that we can tell where the coordinates came from. So the coordinates of P are P1, P2. And so P1 is the x-coordinate of point P, P2 is the y-coordinate. So the same thing for R, R1 and R2, Q1, Q2. So all of the X coordinates are going to have a subscript of 1, and all the Y coordinates will have a subscript of 2. So it's real easy to tell when we start talking about them what point they came from. Okay, so let's look at, remember our slope we said was a ratio, and it's the ratio of the length of QR, or the vertical height of our slope triangle, over PQ, distance PQ, which is the horizontal base of our triangle. Okay, and so we're going to rewrite that because we want to know how can we find this distance QR without having to translate this triangle down to the y-axis and read the height right there. So we don't need to do the translation, but the translation is handy in determining what slope is exactly. But this distance QR can be found by looking at the coordinates. So if we think of this line here that has Q and R in it as a number line, the distance between Q and R is the difference in the y coordinates. So if I had taken these both over to the y-axis, you know, I could do the subtraction right there. But we can do it here because we know what the y coordinates are. So this distance QR is just going to be R2 minus Q2. So I can say that this equals R2 minus Q2. Whoops. Q sub 2. Okay. It's a subscript. Those are subscripts there. So, and then the distance PQ, which I need to find now, is right here. And that's going to be the difference in the x coordinates. So x goes from P1 to Q1. So that difference is going to be Q1 minus P1. Okay, but as we look into computing the slope here, what we want to do is we don't want to have to find the coordinates of point Q because it's not on the line, and turns out it's not necessary to find point Q because we can do all of our calculations just looking at the points that are on the line, P and R. So let's look at a numeric example, and it will become a little more apparent why we can do that. So let's look at this example. There's P, Q, and R. P has coordinates 1, 2. R has coordinates 6, 4. And if we look at Q, it has coordinates 6, 2. So you'll notice that Q and R have the same x coordinate because they both are going to hit the x-axis at 6. This is 6 on the x-axis, so that means on this vertical line here, every point on this vertical line has the coordinate x equals 6. Okay, and so and we kind of saw that when we graphed vertical and horizontal lines. So on the horizontal line here, between Q and P, we'll notice that P and Q have the same y value because every point along this horizontal line has a y value of 2. Okay, so the information that's in Q can be found in R and P. So let's look at how that works out. So we said on the last slide, we said that our slope was equal to this, R2 minus Q2 over Q1 minus P1. So if we want to remove Q from this, we just have to replace it with the value from R and P that it corresponds to. Okay, so let's look at that. So in our numerical example here, R2 is equal to 4. and Q2 is equal to 2. But notice that Q2 and P2 are the same, so I could actually write this as R2 minus P2 over, and now I want to get rid of Q1, but Q1, which is 6, is the same as R1, which is also 6. So instead of Q1, I'm going to substitute R1. And I have R2 minus P2 divided by R1 minus P1. So let's calculate that slope. So we have R2, which is right here. R2 is the y-coordinate of R, so that's 4. P2 is the y-coordinate of P, so that's 2. What do we have here? So R1 is the x-coordinate of R, so that's 6. And P1 right here is the x-coordinate of P, so that's 1. So this slope here, 4 minus 2 is 2, 6 minus 1 is 5, is going to be 2/5. So let's look at that. So what we're saying is that this distance here is 2, and this distance here is 5. So if you think of going from here, an x-coordinate of 1, up to 6 is a change of 5. And if we come right over here to the y-axis, this is 4, and this point was 2. So this difference here is 2, and then we have 2/5. Okay, it's not to scale, but as the diagram is labeled, that's what our results would be. Okay, so just to recap really quickly, this will become our formula for slope, but hopefully you understand where it comes from. So we can think of slope as, kind of the height of the slope triangle divided by the base. Another way that slope is talked about a lot is the rise. How far does the graph rise for a horizontal run? So it's rise over run. Or you can think of it as the difference in the y-coordinates divided by the difference in the x-coordinates. So there's lots of different ways to think about slope. So let's continue calculating slope. Okay, once again, let's look at the case of the horizontal line. So when we have a horizontal line, Q and R actually end up in the same location here. So this would also be Q right there. And if we translated this down to the y-axis, we could read off the slope and it would be 0. So m equals 0 for a horizontal line, which makes sense even with our calculation because the difference in the y-coordinates between P and R, no matter what it is, the difference is 0. Because whatever the y-coordinates are is the same. So this would be over the difference in the x-coordinates. So something like R1 minus P1. Doesn't matter what that is because this 0 in the numerator makes the whole calculation 0. So the slope of a horizontal line is 0, and that makes good sense based on what we know of what slope is measuring. And it also makes sense with the way that we are seeing that we can calculate it. Okay, so what we want to do now is we're going to have a short discussion and then we'll summarize the lesson and be done. But what we want to do now is look at the general case. So this diagram shows any 2 points P and R on our line. And okay, so we're going to show that we're going to kind of do in general what all the examples have been illustrating in this lesson. So we want to look at the slope triangle for this. So let's draw it. I'm going to put some lines on here. So I'm going to draw the horizontal line through P and the vertical line through R. There we go, and that gives us our point Q here. And so we have the slope is going to be the distance QR over QP. But first let's look at the other triangle that we can draw here, where I'm going to draw another vertical line, and I'm going to call this Q prime and this R prime. And I've drawn this so that this vertical distance is 1 right here. So we've got a couple slope triangles going on here. So we have our point Q is an unknown distance from point P, and Q prime is a distance of 1. And so then we've got the corresponding points up here. So like we saw in the example earlier, we have a couple similar triangles. So we have that triangle, we'll write the similarity statement here, triangle P, R prime, Q prime is similar to triangle P, R, Q. Okay, so let's look at where those are showing up. So we've got P, R prime, Q prime right here. The small one is similar to the larger triangle here, P, R, Q. And we know that because of the angle-angle criteria. We've got, they share this angle here. The RPQ angle is in both triangles, and then both triangles also have a 90-degree angle right here. So quite simply, we can see that these are similar triangles. So we know that the corresponding parts, the ratios of the corresponding parts are going to be equal to one another. So we can write those ratios. So one of the ratios we can write is that R prime Q prime over RQ. That's one of the ratios of corresponding parts in those two triangles. Another ratio, and those would be the vertical distances in the triangles. And the other thing that's going to be important for slope is the horizontal distances. So we can P prime Q prime is the base of the small triangle, and the base of the larger triangle would be PQ. Sorry, I've got the prime in the wrong place here. So it's not P prime. There's only one P because they share that point. So it's PQ prime and PQ. So we've got PQ prime, the base of the small triangle, and PQ is the base of the large triangle. So those ratios are going to be equal. We could also write a ratio of the hypotenuse here, the PR prime and PR, but that's not going to be useful in calculating the slope. It's the horizontal and vertical distances that we want. So we're going to notice a couple things. One is that for what we showed in lesson 15 was that this distance, Q prime, R prime, is actually the slope. When the horizontal distance is 1, this vertical rise, this vertical distance, is the slope. So instead of R prime, Q prime, I'm going to substitute M, because that actually, let's get rid of this, is the slope. Okay, so R prime Q prime is M, and QR is that unknown length on our triangle, and that's going to be equal to this other ratio. So we know another distance here. We know that PQ prime is 1, and we don't actually know PQ. It doesn't look like a Q right here, but it is. Okay, so now we have this proportion right here, these two ratios set equal. And so we can take, let me get a different color here. We can take, and if we multiply both sides of this by the length of QR, multiply here times the length of QR, because it's just a number, right? We get that being 1. And so we can see that the slope, M, so this side of the equation over here becomes M, the left side, is equal to length QR over length PQ. I should have the length signs on all of these here. Sorry. These are all distances. Okay, so we're getting that the slope is equal to QR over PQ, which is what we were finding with our examples. But it's nice to prove it in the general case and know that it's true. Okay. Okay, and so from the last slide, let's go back and look at it. We saw that the slope, where did we have that? That the slope could be found by just looking at the, let me get a different color here, right here. The difference in the y-coordinates of the 2 points on the line R and P, and divided by the difference in the x-coordinates. Okay, so right over here, this slope M becomes R2 minus P2 over R1 minus P1. And that's how, in practice, you're going to calculate the slope. Okay, so let's look at the lesson summary. We saw that the slope of a line can be calculated using any 2 points on the same line because the slope triangles that are formed are similar and the corresponding sides will be equal in ratio. And so given a non-vertical line, if you have any 2 points, such as P and R, then the slope of the line is equal to this ratio. And notice that P2 minus R2 is the difference in the y-coordinates because the y-coordinates are labeled with a subscript of 2. And P1 minus R1 is the difference in the x-coordinates, which is labeled with the subscript of R. Not R, 1. So the numerator in the formula is referred to as the difference in y values, and the denominator is the difference in x values. And again, we said it could also be thought of as the rise over the run of a graph. Okay, so you're ready for the exit ticket and the problem set on this. And you should probably check your work as you go along just to make sure that you're getting it. There are a couple problems in the problem set that are going to actually give you a little bit more flexibility with finding slope from a graph. And so go ahead and really take your time with that. Make sure you've checked it carefully and that you're understanding what to do, because this concept is really central to so much of the math that comes after this. So it's pretty important concept. Okay, so any questions, give a call. Otherwise, good luck with that.